So I want to start off with this quote from the Shell the Global Scenario Report, where it says that the global scenarios should challenge individual and more widely held assumptions, so highlighting potential risks and opportunities. So that's what I want to take as my starting point, and I want to take this as the assumption I want to challenge. So when we're looking at Africa, this is the sort of information that we're normally bombarded with: scorched earth, these totally dried up soils and dying crops. Now, I'm not saying that's not a correct scenario, but I want to pose this point. You can also have increased precipitation in Africa in the future. That is predicted. Therefore, we also need to think about this scenario, not just the previous one. So if we look at the IPCC 2007 globals, the predicted precipitation temperature, what we'll see is that, yes, we do have increased temperature. This is increased from present day. We have increased temperatures basically across Africa. But the bottom one here is the precipitation response. And in Northern Africa and Southern Africa, we have an increase, a reduction in precipitation. But look at Eastern Africa. Look at the central equatorial belt there. This is a large increase in precipitation. So very different from the widely held assumptions, or often held assumptions, that everything will dry out. So if we take the climatic scenarios for Africa, we have three. We have it's definitely going to get warmer with reduced precipitation, but we also need to consider about what happens when you have warmer with increased precipitation, and then what about increased atmospheric carbon dioxide, which will be occurring across Africa in all regions. So what I want to do today is to ask what are the range of possible biodiversity responses to these three climate scenarios, and then come on at the end to just say, so what are the potential opportunities and risks associated with these scenarios? So first of all, how do we go about looking at biodiversity scenarios? Now, the usual method is this one here, the predictive output from models, species envelope models in particular. But the second set of data I want to look at is data from past ecosystem responses to similar climatic scenarios. So modelling biotic responses, these are species envelope models that are mainly used, where you take the present day distribution of the species and the present day climatic envelope it's in, then you predict the future climatic envelope and work out where the species will be based. What they mainly do is predict loss of suitable climatic space, and many of the outputs do result in fairly dire predictions. I've just got two for Africa in here. This is one where they looked at 277 African mammals, and they looked at 2050 and 2080. And sure enough, we have these predictions between 25 to 40% loss in these various mammals. The same is also true in South Africa when we look at the fynbos vegetation in particular, that we're going to have 65% species will be lost due to loss of climate space. And we have an extinction of 10% of the Proteaceae family. Very dire. But there are some problems with these models. They're very good in many ways, but one of the things is they are highly sensitive to the algorithms that are used in the models. They're often on a very coarse scale. You're often getting 25 to 100 kilometre square grid scale. They focus on individual species, and when you're trying to plan for landscape planning, that's not actually often that useful. And so an additional approach is to look backwards, to use long-term ecological records at previous intervals in time, to previous climatic scenarios, to predict forwards. So these long-term ecological records can go from looking at pollen, to looking at leaves, to looking at charcoal, and also things like stable isotopes will give you a good indication of climatic changes and various things like salinity and temperature. So what this does is it enables the determination of biotic responses, but determinations that can then be fed into these scenarios. So let me just give you one example. This is East Africa over the last 1,100 years up to present here. And what you're seeing here is that you have the Little Ice Age, where it was relatively wetter. This is present here, relatively wetter than present. And you also have the medieval warm period, where it was significantly drier than present. So this is a aridity measure in here. But when you start to look at the African records, this is a summary of all the different African records that have been looked at, paleo records. You have clear bands of time when it's warmer and drier, and then warmer and wetter. And then when you go back to the last glacial, it's colder and drier. But it's these two bands that are particularly interesting because you can look at the biotic responses and start to look at what does happen to your landscapes in response to these changes. So let's first of all look at decreased precipitation, i.e. the scenario that's been predicted for North Africa and South Africa. So this is a typical pollen diagram here. You just need to concentrate on this part. This bottom band here demonstrates grasses, and this is your other open ground taxa. And as I think 99% of people in the room would expect, as it gets warmer and drier, you get a big increase in the grasses. And you'll see that throughout Africa. In all of these diagrams, as we got warmer and drier, you see this increase, this reduction in the tropical rainforest trees and an increase in savanna and grasses. I won't go through them, but just to give you an indication right the way across Africa, apart from interestingly in North Africa, where you already had a vegetation type that was already resilient to these changes. So you get an increased opening up of the vegetation, you have a decrease in forests, an increase in grasses, and an increase in burning, but only in some areas. And what it becomes apparent is it depends on the ground biomass as to whether or not you have an increase in burning. So let's move on to the next scenario, which is increased precipitation with increased warmth, as is being predicted in the future for East Africa and tropical West Africa. And I think this is where it becomes much more interesting in terms of ecosystem service provision. So what's the evidence for increased humidity and temperature? There's lots of evidence. So this is leaf waxes, and it gives a very good indication of humidity and temperature. And this is present day here, and this is going back to that interval I was talking about. All three sites show this big increase in humidity at that interval in time. It's an independent proxy. So what happens to the vegetation? Well, this is a measure, this is delta 13C, which is a measure of going from grasses, a predominantly grassland vegetation, to predominantly forested vegetation. And as you increase in your humidity, you have a very nice relationship in here. You get a large increase in your forests. Let's take that a bit further. This is 73 terrestrial sites that have a fossil pollen record in here, going right the way across West Africa here. You can see all these small sites here. And this very nice paper, the work was done on here, when they plotted individual taxa, I'll just pick on these four here, but basically if we look at this one here, so this is time going from 12,000 years ago to 4,000, so this is your increase in humidity here. This type here went from 15 degrees, so it was down here, it shifted its range right the way up to 25 degrees north, i.e. currently where it's Saharan desert. And that's true of all of these species. They all have individualistic responses, but they're all moving north in response to the increase in humidity. So just to summarise that quickly, you have a very large range shift of between 400 to 500 kilometres northwards of your tropical forest. At the same time, the Saharan vegetation that was there didn't move. It's remained. Therefore, you've got these non-analog vegetation types, and you've got effectively the greening of the Sahara. So last one is increasing atmospheric carbon dioxide. What does that do? Well, to really understand what that's going to do when we're looking at 1,200 parts per million volume, which is frightening, you need to go back to the early Eocene. Because in the early Eocene, the atmospheric carbon dioxide exceeded 1,200 parts per million. And tropical sea levels here were between 5 to 10 degrees C warmer. What happens to vegetation? This is the interval in time. Great increase in diversity of vegetation. Not a loss. And the same with Africa. But let's look at that at a global scale. This is before the increase in CO2. So this is late Cretaceous. This is the tropical rainforest belt in Africa at that point. This is what it looks like when you have higher carbon dioxide. Massive expansion. It's actually the most extensive interval of tropical rainforests in Earth's history. So what's going on here? Why are we getting this? Well, it's a carbon dioxide fertilization effect is now thought to be. Well, basically, if we look at this picture here, the top one here is a higher CO2. At higher CO2, even at temperatures up to 40 degrees C, you get much higher NPP when you have higher CO2. And basically, it's the whole system speeding up, higher rates of photosynthesis. And it's greater in tropical regions than in temperate regions. And many of the models, the current models that we see, don't take this into account, this carbon dioxide fertilization event. But many of you are probably sitting here thinking, well, 55 million years ago, come on, get real. But so are these realistic, these measures? Well, this is some really interesting work. This work's been done by William Bond. He just lent me this. This is coming out in a paper next month. There's quite a few papers already. He grew some savanna species, this is acacia tree, kept the temperature constant, precipitation constant, and just grew this species, these are the roots, in differing carbon dioxides, values of carbon dioxide, and you'll see what happens, a massive increase in woody biomass. It's not only the roots, you also see it in the shoots as well in here. And what we're seeing in many areas like South Africa and also around Kenya is we're seeing a gradual increase of thicket expansion of shrubby trees taking over the landscape. So this is 1925. This one, the same landscape in 1993, and this is the landscape now in 2001. And this is significant. It's not just happening in one area in South Africa. We're also seeing that's not such a good set of photos. You're also seeing the very, very similar things in here in the Kenya hills. Now, there's extensive work's been done on this. They have ruled out other factors in here, and it certainly seems to be carbon dioxide that's increasing the biomass. So what are the potential opportunities and risks that we need to think about for key ecosystem services in here? So the first one is regulation services. If we're going to have increased forest cover in some areas, then we should be saying, okay, this is important for the carbon stocks, the carbon drawdown that we're looking at. So parts of the Sahara, it's been mentioned before, the sort of green of the Sahara, we should be looking at that. In terms of provisioning services, we could say an increase in biomass in some regions is important for food and for fuel. Some recent studies shown that, in fact, it's not the amount of biodiversity, it's the biomass, the amount of biomass that's important for poverty alleviation. So this could well be an important point to take home. What about the risks, though? And I think this is one of the big risks. Many of the areas that are currently being eyed up, primed up for being important for biofuel production are also the areas where those trees would, in a future scenario, be moving into. So I see that as a large risk. But also the other point to make, this is the same sort of thing, looking again at this increase in woody cover in South Africa. You'll see that it covers all three. It covers the commercial ranching, it covers communal rangeland, and it covers protected areas. So it's happening in all three different, it's not just in one of those bands in there. So what does that mean? That means that in terms of provisioning service, you're getting a loss of grazing land. This could have significant implications. In terms of cultural services, you're getting a loss of tourism. Certainly in Kruger now, they're starting to look at this as a serious problem, as woody encroachment and the loss of savanna and the open environments. And finally, there is a problem with the regulation service because you are significantly changing your surface albedo as a result of this. So just to conclude, I think that we need to really look at this on a spatial scale. The responses are highly regionally specific. And in terms of ecosystem services, there are opportunities, but there are also risks. But the important point is when you're scenario planning, these do have a predictable spatial landscape scale. But, and this is a but, we don't currently have the landscape planning tools to map and evaluate these different scenarios. And without those landscape planning tools, the people are working in a void. I can stand up here, give you this data, but likewise, unless we really do know and are able to map and think about these things, then we'll just go and destroy the areas that really have the greatest potential in the future for ecosystem service provision. And I would emphasise that point by saying that many of the land policies, or maybe particularly the biofuels, I'm sure there are many others as well, though, that are based only on the current state, could pose significant risks for future ecosystem service provision. And that's something I certainly would like and hope that this will be discussed in the next day. Thank you.